So I'm going to talk about parallelism and about our approach for trying to make parallelism easier. So just a short presentation. I come from University Carlos III in Madrid. It's a young and a small university, and I work in a computer architecture group. So we mostly work on parallelism. I work in a line of programming models for application improvement. So I'm concerned about performance, energy efficiency, but also maintainability and correctness of software. And for the last 10 years, I have been representing Spain in the ISO C++ Standards Committee. So the library I'm going to present today has been funded by one European project, the Reface European project that finished last month. And we already got funding from another European project for the next 3 years, and we also had some national funding. And also to mention some people that has been working in this project, mostly in my university, but also there is one person at CERN in Switzerland and some other persons in University of Pisa and University of Torino in Italy. So let's go to the thing. What I am going to present has to do with design patterns for parallelism, something that some people also call skeletons, and that is highly related to the philosophy of the STL. So if you think about sequential programming, in sequential programming we have a set of very well-known control structures, the selection, loops, and so on. The problem with these control structures is that all of them, they are inherently sequential. Now, when you go to parallel programming or to traditional parallel programming, what we have mostly are constructs that try to adapt and try to contort the already existing sequential control structures to the parallel world. And probably the best example of this is the OpenMP parallel for. You had this for loop that where we had introduced sequentiality, so first iteration, second iteration, third iteration, and now you try to convince it to become a parallel control structure. Now, but what if we had constructs that could be both sequential and parallel? So we tried to think about this, and at the same time we tried not to invent a new programming language or a domain-specific language. So I like a lot this quote. There are two ways of constructing a software design. One way is to make it so simple that there are obviously no deficiencies. And the other way is to make it so complicated that there are no obvious deficiencies. This is something from Tony Hoare, and the first method is far more difficult. So my feeling is that continuously when we do parallel programming, we are using the second method. And this is why it is so difficult to find some bugs in our parallel programs. So this is a small example of something that I can do today. So if I want to add numbers that I have in two vectors and produce a new vector, I would have this for loop. Now, this for loop is sequential, but if I think in the nature of the problem, there is no sequentiality at all. I could do in any other order, and that would be also okay. The problem is that I am introducing additional constraints to traverse the vectors in a specific order. And this also opens the door for potential mistakes. Now, if I do it the STL way, we have today STD transform. And I can, now I don't see this sequentiality so obvious. And it seems it's less error prone. I could do it also with a range base for loop, but again, this introduces sequentiality. Now, the idea of design pattern is not new. Many of you may have gone through the book from Gamma and the Gang of Four, which is very well known and that introduced design patterns in software. Although the idea is older than that, in the 70s, Christopher Alexander introduced this idea for building and for designing cities. Now, in year 2012, McCool, Reinders, and Robinson wrote another influential book where they took the ideas of design patterns from the 90s to the domain of parallel programming. We strongly follow most of those ideas in this work. So we had some ideas in the design of our library. The first is that applications should be expressed independently of the execution model. So I should be able to write my application regardless if I want to run sequentially or I want to run in parallel. That should be a detail, not something that is pervasive in all my code. Computations should be expressed in terms of structured composable patterns. So this is a second idea that is something that usually I don't have in many parallel programming primitives, the idea that I should be able to compose my parallel structures. The third idea is to have multiple backends and a simple mechanism to switch between all those backends. So today in our library, I will show you in a moment, but we have a sequential backend. We have one backend that is underneath OpenMP, another one that is IntelTBB, another one that uses another runtime called FastFlow, and another one which is exclusively implemented in terms of ISO C++ threads. Also, the interface should integrate easily with modern C++ and the standard library. A library with a set of different execution policies and a set of type-safe generic algorithms. Currently, it requires C++ 14. We have tested with GCC and CLang. And currently is a GPL version 3 library. So, and let me call your attention, this was presented for somebody else in a workshop I was this year, and they are using our library now to teach parallel programming in University of Pisa. Okay, so let's see some example. So let's say that I have a sequence of frames and I want to generate a new sequence of frames where each frame, which is an image, is transformed to grayscale. So essentially what I have is some type frame and I have a function to convert to grayscale, and I want to apply the same process to all elements in my container. Okay, I could do a traditional explicit loop where my range for loop goes through every element and applies the transformation. Or I could do an STD transform. This is still the sequential version of STD transform. Or I could do, if I am in C++ 17, I could do an STD transform and use the STD par execution policy. Okay, but in our library, you can use the pattern map, which is quite similar to a transform. Very, very similar, so it has very little differences. And just use one of our policies. This is the sequential policy. So if you compare this with the parallel STL, there is really nothing new. Or you can use here a lambda, of course. Now, this is just a very simple example, and in this example, there is not a huge difference with what you have in the STL. Now, let's go to some details, and I hope to show you examples where we can do different things. So we have a number of execution types which are just encapsulate different ways of executing the algorithms. We have the sequential execution. We have an implementation that we call native, and is basically implemented in terms of the ISO C++ threads. And the idea is that probably if you have OpenMP in your platform, OpenMP will perform better. If you have IntelTBB in your platform, probably it may also perform better. But if you are in a platform where you do not have available any of them, still you can run in parallel with the only requirement that your platform has a C++ 14 compliant compiler. And you also have the fast flow runtime that is runtime some people is using, and that offers a number of low-level patterns. So switching between these different execution policies is as easy as changing the first argument to any algorithm. And we also have a dynamic execution that allows you to decide which is your execution policy at runtime. Some of these execution types allow you a finer configuration. For example, on the concurrency degree, your interface will allow to say which is your concurrency degree, how many hardware threads you are going to use. This has some defaults. The sequential, of course, is one. And for example, in native, we take the hardware concurrency. We are planning some new execution policies that they are not yet available in the current implementation for allowing execution in CUDA through CUDA Thrust, or in OpenCL through SYCL, and also a distributed version that will use MPI underneath. But this is still work in progress. So what patterns do we have? We have data patterns, and here we have the map, the reduce, and the map reduce, and also the stencil, which is a pattern that you do not have easily accessible in the current STL. We have one task pattern for the divide and conquer, and then we have what I think is a bit more different, the streaming patterns based on the idea of a pipeline and a set of operators like farm, filter, reduction, and iteration. So if we go to data patterns, all data patterns performs operation on one or more data sets that are already in memory. So my input will be one or more data sets and some operations. So, and the output will be different. For example, for map and stencil, the output is a new data set, while for reduce and map reduce is just a single value. So the first one is the map, which is essentially what in the STL is the transform. which applies an operation to every element in a data set. This could be unidimensional or v-dimensional, or in GrPPI can be n-dimensional, while the transform in the STL can be applied only to one data set or two data sets, but not to 3 or 4 data sets. So this is a very simple example, doubling all elements in a vector. If I want to do sequentially, I just pass the sequential policy. But basically, I provide iterators to begin and end, and where I want to leave the result. So this is the same interface by design that a transform. If I want to run this with OpenMP, the only thing I need to do is to change my execution policy to the OMP execution policy, and that's done. Now, if I want to use with more than one dimension, we diverge from the STL typical interface, and what we take as a second argument is a tuple of iterators. In this way, we can pass 2, 3, 5, whatever. So this is a map or a transform that takes 2 vectors and then add each element of one vector from the other vector. But if I wanted to do with 3, I also may do it with 3. I have a tuple of 3 iterators, and then my lambda, of course, takes 3 values. The result of a transformation can be from a different type. So in this case, I am taking 2 vectors of doubles, and then what I am producing is a vector of complex values. And my lambda just creates complex double values like this. The second algorithm here is a reduction that combines the values in a data set with some initial identity value and produces a result. So for example, if I want to add all the elements in a vector, I would do like this. I have GrPPI reduce. I pass the execution policy, the range with my begin and my end, the initial value, and the combination algorithm. Yep?
What are your requirements on the iterators for the different execution policies? So do you need random access iterators?
Right now, we need random access iterators, especially for OpenMP. Yep.
Does that include contiguous? So does it only work with vector, or would it work with the deck?
Should work with a deck because we advance iterators in terms of advance. So that should, I have not tested that, I have to recognize, but it should work. Then we have map reduce, which is just a 2-phase algorithm. It's the same that transform reduce in the STL. Again, we have a first phase of map where I may have 1 or more data sets. The only difference we have with the transform reduce from the STL is that, again, we allow a dimension higher than 2 for the map phase. And then we have the reduce phase. And the idea, as in the STL, the idea of having a different map reduce instead of doing map and then reduce is that you can fuse both operations and you have access to extra optimizations with some backends. So this is the idea of the map reduce. And I can use the map reduce, for example, for taking a vector of doubles and computing the sum of its squares. So my map stage would be squaring values, my reduce stage would be adding two values. I could use this also if I have a vector of shapes for adding the areas, and then the map stage would be compute the area of a shape. The reduce would be adding values. The scalar product between two vectors can also be computed like this. An example that I like especially, and that can be also implemented in terms of transform reduce, is what I call the canonical map reduce example. Because every time somebody talks about map reduce, I see this example where you have a sequence of words and you want to compute the frequency tables of the words in some text. So let me show in this example, I have an execution policy and I have a vector of strings. So the first thing I am going to say, just for brevity, is that a dictionary type is a map of a string and an int. And then I'm going to map reduce my sequence of words using as identity value the empty dictionary. And then my map phase would be, I take one string and I produce a dictionary having only one word with frequency 1. And my reduce phase is I take two dictionaries and I merge them, adding values for those that have a common word. That's it. We have also, and this you don't find in the parallel STL, the stencil pattern. The stencil pattern is quite similar to the map, with the difference that you use in your computation not only the element of interest, but also some values in the neighborhood, by some definition of neighborhood. So as we do it is to stencil, you pass the range, and then you have your function that takes an iterator and a neighborhood and performs the computation. And you need to provide a second lambda which computes which is the neighborhood. So giving an iterator, I have decided in this example that my neighborhood would be the previous value and the next value. So for each element, this lambda is going to return the neighborhood. Yep?
Can the neighborhood be a view of the original container, or does it have to be?
It can be whatever. The only thing that you need is that what you return here and what you take here match. So, yeah, and it's a good idea in many cases that it is a view because it will be much faster, of course. But we do not have any special requirement on that. Okay, so this is probably the less interesting part. We have only one task pattern for the divide and conquer algorithm. So the idea of divide and conquer is I have a problem, I divide into subproblems. When I have problems that are simple enough, I solve them, and then I start combining the solutions. So we have three key elements: the divider, the solver, and the combiner. And it's not a surprise that the three of them will be different lambda functions. So as an example, I will show you how we can parallelize the merge sort algorithm. So just some helper thing, I define a range as a pair of iterators first and last. And here is my constructor. From a vector, I can construct a range with begin and end. And I can also compute the size. That's all what my range has. And I have an additional function that where I provide a range and I divide it into subranges. So I return a vector of ranges, or could be a pair of ranges, of course, with the first subinterval and the second subinterval. And here is my merge sort. So my first thing in divide and conquer will be I pass the whole range of the vector, and I have my divide phase, which is I take a range, and if the range is of size 1, then I'm done. I return that range. Otherwise, I divide the range and I return the list of ranges. Now, once I have a unit range, a range with a single element, it is already sorted, so I just return the value. And when I want to merge two ranges, I just use std in place merge. And I return the new range, which is from the first element from the first range to the last element to the second range. And this works nicely in my multicore, and all the details are orchestrated by the library. So what I think is the most interesting part of the library are the streaming patterns. So the basic idea of streaming is using pipelines. If you were this morning in Detlef's talk about executors, he showed some examples of pipelines. Our approach here, you will see, is slightly different also, although the basic ideas behind are probably the same. So the idea of a pipeline is having a computation divided in stages. So the first stage produces values, send these values to the next stage, which produces new output, go to the next stage, and so on. And this is something that can be very easily parallelized, provided that you have the proper communication mechanism between stages. One example of this, very typical, is video processing, where you have a first stage that is receiving frames, and then the next stage will apply a filter to the frame and pass the result to the next stage that may apply another filter and so on, and then finally the last stage will write again on disk your processed images. The most simple pipeline is just a standalone pipeline. Invoking this pipeline translates into starting the execution of the pipeline. So basically, I need a function that I will call a generator, which is any lambda that takes nothing and produces values, and then a sequence of transformers that take values from one type and produce value possibly from a different type. So basically what you are doing with the pipeline is performing the composition of all these transformation functions to every element produced by the generator. So which value should the generator produce? Well, the generator is a function or any callable entity that takes no argument and returns a value of a type that might hold or not a value, because we need some way of signaling the end of stream. So we decided that we produce a value or not, and then the null value means we are at the end of the stream. So the return value of this generator needs to have some properties. The first one is that it should be either copy constructible or move constructible. Also, it should be contextually convertible to bool to check if it is null or not. And we should be able to dereference the type. Well, you probably know some type that fulfills these requirements. optional. It's not the only one, and you can use your own type. We do not require in any way that you use optional. You need to use something that behaves like an optional. A pointer. But then you need to take care about memory management, and probably the performance is not going to be as good in some cases, especially for very simple values. Okay, here you have a pipeline. So if I want to run a pipeline, I call pipeline with some execution policy, and I just put a number of lambdas. That's all. The only thing I need is that the first one returns something that is optional-like, and then we need to have matching. So if this returns an optional of int, the second function will take an int. And if this function returns a double, this function takes a double. If this function returns a double, this one takes a double. So we make this kind of type checking internally. And the other thing we decided is that after your first stage, optional or the optional like, you do not see anymore it. So because we think this is the simpler interface for the programmer, and we try to address an interface that tries not to be for experts. We can also perform pipeline nesting. So I can say that one stage of a pipeline can be itself a pipeline. So the only difference is that for internal patterns that we can put as operators in a pipeline, we do not usually give an execution policy. And then we inherit the execution policy of the container pipeline. So that means that inner pipelines do not take execution policy, that they do not have a generator, and that the last stage need to produce data for the outer pipeline. So for example, here I have a pipeline, and then I have my generator, which essentially reads one frame from a file and returns either the empty object or the frame I have read. And then I have an inner pipeline with two stages. The first one just performs a filtering. The second one performs a transformation to grayscale. And then I am again in the outer pipeline, and I have a last stage that writes on disk. So the idea of these inner pipelines is composability, because I can express my structure better, but also because I can express this by defining lambdas somewhere else.
Where's the parallelism here? How does it actually benefit from this compared to just having a single lambda that does everything sequentially?
Because the executor is going to spawn different threads for every stage.
For every stage?
Yes. And then we will have underneath some communication mechanism, which will be some multi-threaded queues that might be log-free or blocking depending on the case.
If the stages are simply linear composition of functions, where's the benefit of spawning multiple stages for the same linear composition instead of a single thread that does everything at once?
Because you are executing them in parallel, especially if these are heavy functions. I mean, the benefit is that you are running the different stages in parallel, so at any point in execution, each thread or we will see that I can assign more than one thread to a stage. Each thread is performing computation with a different data item, so all of them are running at the same time. Did I answer?
Yeah.
So, confusing. Is it that this composition pipeline, both of those will run in parallel? Or
In this case, it doesn't matter this composition pipeline. If I go to my previous case, where I have it linear, it's going to be the same thing. Every stage is going to run in a different thread. So the reason for having this, I will show some example at the end, is that I may decide to use a different execution policy for this subgraph in the whole pipeline. Yeah.
One of the things with the video pipeline and streaming is to make sure that you get a handover between the elements in sequence. Have you done any work on that?
Okay, I was going to mention this later, but we provide, depending on your application, you may run in two modes. One where we preserve the ordering, another one where we don't want to preserve the ordering. And I have a use case where we could not preserve the ordering just because the different data items had individual identifiers, and we got an additional speed up because of that. So you may, it's your choice. When you configure your execution policy, you may say this kind of thing. So we don't have 100 knobs, but we have some knobs.
You mentioned that each stage will be run in a different thread. Does that mean that every stage...
Well, to be correct, sorry, in some execution policies, that's true. For example, in IntelTBB, that's not true.
Okay. I want to ask, every lambda I put in,
Yeah.
can I expect it to be run by those one thread, or can the same lambda be run concurrently? Meaning,
No, every lambda, so this lambda will be running all the time in one thread. This lambda will be running all the time in a different thread.
so they could have modifiable state internally, and that would not be a problem.
Yep. Okay. So, of course, I can do this in a different way, which is defining my lambdas like this, and then I call my pipeline in this other way. We have found that some people felt more comfortable with the first approach. Some people feel more comfortable with this approach. Especially, we have some users that are C programmers or C-like programmers, and they feel much more comfortable with this approach. So both approaches are possible. In fact, there is nothing that prevents you that one of these stages is not a lambda, but is just a C function. Okay.
I think the stronger argument for this separation is that you can provide a library that has part of the pipeline and
Yeah. For example, something that comes very easily is providing as a library a number of generators that read from specific file formats and a number of consumers that also write in file formats. Yes, absolutely. Okay, so the next oh, sorry.
Sorry, just the question. Now we're talking about image processing. Sometimes you start having to differ in the pipeline. It's not only a straight line. Sometimes you have to do some size and start generating different things, because sometimes you're going to send it through, I don't know, you're going to publish it in HLS and be available for the user and storing it there archive at the same time.
Okay, we have some options, but not so general. So the idea is that what we have is a pipeline. What we don't have today, it's in our shopping list, is a generalized graph. But we don't have a generalized graph today, although we have some things. So one of the things that we have is a farm. Farming a stage is stating that I want multiple threads for this stage, because probably this stage is heavier and it's going to take too much time, and the global speed up of a pipeline is limited by the slowest stage. So naturally, if you have a very slow stage, you want to replicate that stage. So this is what we call a farm. So I may have here a farm for this lambda. This is telling me that this stage will have 4 threads, 4 replicas. And in this way, I can, yep.
Just for clarification, this will not get the same input. So it's not that one frame.
No, it's not getting the same input. Each thread, when it is not busy, it will get the same element from the next element from the queue. So we are sharing work, yes. We are sharing work among threads. And this is when what I mentioned previously comes out, because then it might happen that at the other side of the queue, here, values would come in a different order. So by default, I think by default we do order, which means that we preserve order. But if you want, you can say, okay, I don't mind order, just do as fast as you can. It's your choice. In fact, when we say this, even if you say ordered, we do it in a way that we just reorder at the end of the pipeline. Yeah. So that in the middle we can go as fast as we can. So this was a farm. And this was a farm in a different way. I just can say, okay, I have my improver, which is not a lambda, but a farmed lambda. And it will work. So we have the ordering, which implies a time stamping of items. And then to my execution policy, I can say enable ordering or disable ordering. We have some additional properties because we communicate, usually not in every backend, but in most backends, we communicate different stages with queues. These queues have a queue size. We have a default queue size, but you can change it. And it has a default mode, either blocking or lock-free. And it depends on the application. Our experience is that depending on the application, it might be that your application goes better with blocking queues or with lock-free queues. There is no a general true answer to this. Another operator that we added is a filter. A filter is something that is going to discard or to keep some data items while the rest are gone, and this is based on a predicate. And this is something that I can put as a stage of a pipeline. And this means that you can produce many items, and then at the end of the pipeline, you get less items. We had a strong discussion if what would mean filter, filtering or filter out. And then when we showed code to people, different people read the code in a different way. So at the end, we decided that the right answer was to have 2 functions, keep and discard. So keep only keeps data items satisfying the predicate. Discard only data items not satisfying the predicate are sent to the net stage. So here you are. Here, for example, we are producing numbers, and then we decide to keep only prime numbers. So it's as easy as keep and my predicate. Or here I'm deciding to discard those words whose length is less than 4. Okay? Then we have stream reductions. When we perform a regular reduction, we need to have the whole data set. But when we are in a stream, especially if data is coming from the network, for example, what you want to do is slightly different, is to perform reductions on windows of values. So for example, every 10 values, I compute the average, or whatever. So for this, we have these reductions that take a window size and also an offset. However elements I start a new window. So in this way, we allow both non-overlapping windows and overlapping windows. And then, of course, we have an identity because it's a reduction operation, and we have a combiner. So here, for example, I'm getting numbers, and I am computing reductions, which is adding all those elements in windows of 100 elements, starting a new window every 50 elements. So those are overlapping windows. And the last operator that we have today is stream iteration. Stream iteration allows you to have a subset of the pipeline to work as a loop. And this is sometimes useful if you are processing elements and then you have some quality metric, and if the quality metric is not satisfied, you feed back that data item and you reprocess it. So we have a transformer and a predicate. Okay. So here you have this pipeline with a generator, and then I say repeat until. I think easy to understand. I repeat multiplying my value by 2 until it's greater than 1024. So I may have, so this is not exactly, this pipeline is not exactly acyclic. We allow sometimes of cycles to do feedback, and yep.
The repeat until, does it take pipeline as the first argument?
No,
In general?
no, it takes one stage. Now I put a lambda. Nothing prevents me to write there an inner pipeline, and then I'm done. So we try to find a number of operators that were minimal and composable. And this is the way, if you want to have multiple stages, is like you do.
So in this case, it feeds back the value at the parent pipeline. So if you have multiple nested pipeline, and you have a loop in the nested one, it's going to...
Yeah, only there, yeah. So, for example, we have found that this could be used in some learning algorithms easily because of the feedback. Okay, and then finally, another thing that we have is context, multi-context pipelines. The idea here is that sometimes you have your long pipeline and you don't want to use the same execution policy all the time for all the pipeline. So whenever you want a subset of the pipeline that you want to run with a different execution policy, you just say run with and this new execution policy. This has a number of issues or of uses. First one is that now, even if I have the same execution policy, let's say OpenMP, I may have two OpenMP execution policies with different number of threads. And then in this way, I may decide to give a number of threads to one subset of the pipeline and another number of threads to the higher level pipeline. This is one use. Another use that is not today, but it is planned, is that this simplifies a lot when you want to run a part of the pipeline in the CPU and another part of the pipeline in the GPU, because then you have just a different context with your GPU execution policy, and then all the internals of the library is going to take care about the communication between the CPU and the GPU, sending data, receiving data. And this again tries to simplify as much as possible the view that the application programmer has of the model. So I'm not going to give you here a very long evaluation, but just some data. So the first example I'm going to show you is a small example of video frame processing for border detection. And for this, we use two consecutive filters. The first one is a Gaussian blur, and then a Sobel filter. So the idea is that I have 4 stages in my pipeline. First one is just reading a frame. Second one applies a Gaussian blur, and I might decide to farm this stage. The third one is the Sobel filter, and again, I might decide to apply a farm or not, and then finally writing on disk again. So there are 2 questions here to answer. How much difficult is to write the program? And what about performance compared to performing this parallelization by hand? So both in terms of number of lines of code and in terms of performance. So we used the manual approach and then using GrPPI. Okay, so this is a very rough estimate of the number of lines of code that were added over the initial sequential application. So you may see with C++ threads, okay. The first line is just a normal pipeline. The second line is a pipeline where we have a farm in the second stage. The third one, we have a farm in the third stage. And the fourth one, we have farm in the third and fourth stage. Now, when I write this, spawning my threads and using my queues by hand, obviously I have a lot of lines increase because I have to manage my threads, I have to manage my queues. And this boils down to around 60% for one farm, around 100% for 2 farms. We did again this with OpenMP, and with OpenMP, the results were quite similar, because if you want to use a pipeline with OpenMP, okay, you have OpenMP tasks, but still for communication, you need to write your own queues or use some queuing library. Now, in the case of IntelTBB, it's always the same cost, because IntelTBB has its own pipeline. However, you have to write more for using IntelTBB pipeline, because you have a number of extra details. So it was around 25%. This is yep.
Does it allow you to use farm?
Sorry?
Does it allow you to use the farm concept?
Yes, approximately.
Okay, but there is no difference.
There is no difference because the source code is the same. Basically, what IntelTBB is going to do is you don't explicitly say farm, but this is configured by the number of tokens in IntelTBB. And then we have FastFlow. FastFlow, it has the concept of farm. But still, you need some effort between 16 and 39%. Okay, and this is GrPPI. So in terms of line of code, essentially we just took the sequential code and here and there decided, oh, this looks like a lambda. Okay, I'm done. So the cost is quite small. So the second question is performance. So what we are representing here is a different resolution, image resolution, how many frames per second we are able to process. So this is the original pipeline. This is the pipeline with farm in the first stage, farm in the second stage, and 2 farms. Of course, this goes at a higher scale. But what is relevant for us is that the difference between manual implementations and GrPPI implementations, we lost a little bit, but it was always below 4% in terms of performance. So we think that we still can optimize more the library and get rid of this small overhead. But anyway, we also think that this is compensated by a much lower effort in terms of development time. The second thing we did is a larger application. This is a brain magnetic resonance imaging application using a hospital in Spain, which tries to get very detailed information from the brain. So the idea of the application is that this is then used for diagnosing mental diseases. Especially this is trying to find by physiology disorders like bipolar, paranoia, or schizophrenia that today are usually diagnosed by symptoms. And they are trying to be able to diagnose in a physiological way. So for this, a very important thing is to identify fibers and connectivity between areas in the brain. So basically the result, you take the magnetic resonance that, depending on the resolution you use, might be between 100 of megabytes and a few gigabytes per patient. And what you want to produce is something like this. This is a brain. This is a brain in terms of connectivity, so what you are following is just the trajectory where the communication between neurons is going through your brain. Okay, so this is what we produce. And for this, we set up a pipeline with 1 stage for reading the huge file where you are slicing the brain, and another stage where you are producing your results. And in the middle, we have the processing stage, which is farmed. So what we are representing here is what is the cardinality of the farm, starting from just farm 1, which is all the processing in 1/3, up to a number of like 19, 20 threads for the farm. Interestingly, in this case, we could perform processing without ordering, because the image format that is used by the MRI machine has an identifier for every slice. And then you will write every slice in the right place in the output file. And in this case, because not all the slices requires the same amount of processing, it's especially useful to be able to write in not ordered way. So, this is the sequential cost. This is a low resolution image, about 100 megabytes, and requires sequentially a bit more than 900 seconds. And then Blue is, sorry, this is blue sequential. This one is TBB, that where we got very good results. With threads, ISO threads, we got bad results for 1 or 2 threads, but as we increase the number of threads, we approach and we converge with IntelTBB, with OpenMP also, and right now we have slightly worse results with FastFlow. Interestingly, this is the last execution policy that we have implemented, and probably still there is a space for improvement here.
What I don't understand is why even for the single thread case, the sequential version is much slower than some of the others. So is there some parallelization or what happens here?
Well, the computation part uses some vectorization and some linear algebra parallelization. But this was in the original application, and this is another interesting thing. We do not touch the original application. The original application uses Armadillo and other libraries that uses already parallelism for linear algebra. Yep.
What number of cores does the machine that was tested on have?
24 cores.
24 cores, okay. Is that logical or physical?
Physical. Yep.
What considerations and problems do you have with caches? We've done something similar. We found that caching performance has influenced things considerably.
Sorry, again.
We've done something similar using pipelines and TBB. We found that caches has been one of the biggest penalties as far as slowing us down. Have you come into this when you're doing this work?
Okay. So the question was caches, and yes, probably cache hit rate was slightly worse than when for other approaches worse than for TBB. And the reason behind that is because TBB tasks tend to be reused so that you go from one stage of the pipeline, from the next stage of the pipeline, but you keep living in the same thread all the time. And in this case, you increase your hit rate, while we are not doing this. Separate stages run in separate threads. So here, but as you may see, this is a difference for a low number of cores, but as you really increase, this difference starts to disappear. Quite large in this case, so it's something that, is quite, the size of data items in this case is quite large. I do not know by heart, but take into account that a single byte would take hundreds of megabytes. So each individual data item is much larger than even the size of L2 for sure. So you will need to go to L3 much frequently.
How many stages do you have in the pipeline?
In this pipeline, we have 3 stages. The thing is that the second stage is farmed until 19. So because we have the reading stage, then we have the computation stage that at this point, we did not exploit. we could still see if we can do more there, and then we have the right stage. So the thing here also is that what we did was easy parallelism, thing that you can do in 1-2 days. And I think this is also a relevant thing. Of course, we still can fine-tune more this application. Yep.
So when you say number of threads, 1, does that mean that you had your farm stage in there and you have 1 thread?
Yeah, that is that the farm has 1 thread, not the whole pipeline. I still have 1 stage for reading, 1 stage for writing. So this is the number of threads for the intermediate stage.
So you're still doing multiple things in parallel.
Yeah.
That's why even.
Yeah. Questions? Okay. So some summary. So we try to present here a unified programming model for sequential and parallel modes. There are multiple backends available. There are more to come. And we also plan to extend this pattern set. We have some data patterns, we have one task pattern, and we have some streaming patterns, but we are planning to add much more operators and patterns to this library. A number of things that we plan to do in the upcoming months is integrate additional backends, CUDA, OpenCL, and MPI among them. At some point, we should eliminate all the awful metaprogramming. But if we do that at this point, which I would love to, and use concepts, then we would restrict you to use only GCC. At some point, we will do that. Extend and simplify the interface for some of the data patterns. I think we can do more things there to make things simpler and probably better alignment with the ranges library. We did some experiment also with supporting non-uniform memory architectures in the native backend. We didn't deploy this yet, but we had some promising results, for example, using as a NUMA device Intel Xeon Phi. More patterns and more applications are to come. So that, in case you are interested in details, in the slides you will find some references, and this is the URL in case you are interested to try out. So that was all. Thank you very much.